I'm Safe. I'm Zach. And I'm Jude. And our end of semester project for ELCT201 was to build an audio digital filter. The main goal of this project is to make the LED display that indicates the high frequency and low frequency on two separate channels using digital filters coded on the M-bit microcontroller.
A digital filter uses a digital processor to perform a numerical calculation on sampled values of the signal. The processor must be general-purpose computer such as PC or specific DCP digital signal processor. The analog input signal must first be sampled and digitalized using an ADC, analog to digital converter. The resultant binary numbers representing successive sampled value of the input signal are to transfer to the processor, which carries out numerical calculation on them. These calculations typically involve multiplying the input values by a constant and adding into products together. Then the DAC, digital to analog converter, to convert this signal back to analog form. High pass can be achieved by which taking the current and second previous input and subtract them and divide them by 2. The low pass filter has three-term average equation which takes the sum of the current and two previous input and divide them by 3. Both of the equations create numbers to represent the frequency. Advantage of using digital filter. When a digital filter is programmable, for example, operation is determined by a program stored in the processor memory. This means the digital filter can easily be changed without affecting the circuit hardware. Analog filter can only be changed by redesigning the filter circuit. Two digital filters are easily designed, tested, and implemented on general purpose computer or workstation. The third one is the characteristic of analog filter circuit subjected to drift and dependent on temperature. Digital filters do not suffer from this problem and so are extremely stable, which represent both to time and temperature. Unlike their analog counterparts, digital filters can handle low frequency signal. As the speed of DCP technology continues to increase, digital filters are being applied to high frequency signal in the RF radio frequency domain, which is the past was exclusive preserve of analog technology. Digital filters are very much more visible in the ability to process signal in the variety of ways. This includes the ability of some types of digital filter to adapt to change of the characteristic of the signal. The last one, fast DSP processor, can handle complex combinations of filter in parallel with the cascade series, making the hardware require relatively simple and compact in comparison with the equivalent analog circuit.
So the first thing you have to do when coding on the embed is assign your pinouts with names and functions. We use this analog out setup here for what we called was a straight through method. This method allowed for us to see the sine wave coming in, apply a filter to it, and see what happened after the filter was applied. This allowed us to dial in our filter to a more precise value. Here we have our floats assigned. Y0, Y1 are going to be our values we get from our digital filters. And these X values here are going to be the sound wave input values. This commented out section here was what we used to have teraterm display values. The reason it is commented out at this time is because teraterm does not allow the embed to function to its highest ability, meaning you drop frames, you drop readings when TerraTurb is running because it takes data or takes ability away from the embed. We implemented two onboard digital out LEDs. These LEDs are onboard the embed. One would flash red when your high pass was on, one would flash blue when your low pass was on. The low pass filter was built using an average term filter. Y2 is the most recent value of Y0. This is called a recursive method. We use this method to get a more precise value of Y0. The reason that our Y0 values are so drawn out is that we wanted to have a tight window for our cutoff frequency. As you can see, when low pass is 1, the blue LED pin out, or the blue LED signal is 0. This happens because the onboard LEDs are current syncing, meaning they must act as a ground in order for the LED to light up. Here we have the reassigning of values so that new data could be collected. The high pass filter was just a simple difference filter using x2 minus x0 divided by 2. This 0.028 value was found using TerraTurb. From the value TerraTurb gave us, we just had to plug values in to get the precise cut on frequency we wanted for the high pass. Here again we have reassigning, and all of the filter equation information we needed was acquired from this website right here.
For the circuit of this project, we inputted an analog signal through a speaker across a diode, which functioned as a noise cancelling element. Then it was jumped to an analog input, which is PTB0. The ground pin of the embed was jumped to the negative bus of the breadboard to have a common ground for all the circuit. PTA 13 for low pass digital out and PTA 5 for high pass digital out were jumped to the base of one of those 7 transistors that were used as switches to power one of those 7 LEDs that were later switched to LED strips for the actual display. 12 volt DC was inputted across the positive and negative buses to be able to power the LEDs. The embed was powered separately because 12 volts would damage the embed circuit.
So I'm Zach.
I'm safe.
And I'm Jude. This is our digital audio filter. Thanks for watching.